My name is Wyatt Joyner. I'm a solutions architect with TigerGraph. I've been working here since April, so pretty fresh, but I've learned a lot, and now I'm ready to impart some GSQL knowledge. So as a solutions architect, half of my job is investigating, researching algorithms and implementing them. And the other half is interfacing with customers. And a lot of these customers are switching over from a traditional relational database to a graph database. And with a graph database, especially with the query design, you're not looking at a relational algebra like you are with a declarative language like SQL. You're dealing with, at least in TigerGraph's case, GSQL, which is a high-level programming language that feels a lot more like writing in other high-level programming languages like Python or C++. So in this presentation, I have a couple use cases planned. And we're just going to go through it. It'll be a bit like TigerGraph with Bob Ross. So no mistakes, just happy little schema changes. And I know at the end of this presentation, we'll have a Q&A session. There will probably be a couple moments when we're waiting for things to install or waiting for the instances to set up. In those moments, we can also answer some questions that you guys have. So as this page forebodes, we're going to be using TigerGraph Cloud. This is TigerGraph's platform for provisioning cloud instances, either on AWS, Microsoft Azure, or Google Cloud Platform, and it comes with TigerGraph pre-installed. And I sent a message about this earlier in the feed loop chat, so you can also see the setup instructions there. So you're going to want to create an account or log in. I think I already have one with my TigerGraph account. And once we're logged in to the TigerGraph Cloud portal, we're going to want to navigate to Solutions. I have here a solution I've already provisioned, but if you don't have this solution provisioned, you're going to want to go to Create Solution. 3.1.5 is fine. And we're going to want to use Entity Resolution MDM 3.1.5. That's the starter kit that we're going to be using. It comes with a nice schema that we can start out with and a couple queries that we can optimize and modify. You're going to click on Next after you've done that. And all the default parameters are fine. You'll want to select a region that's closest to your actual location to minimize latency. I'm doing AWS here, and you want to click Next again. You can set up these however you want. Name your solution as you will, tag your solution, and then set up your subdomain. And it says here all the specifications for what that needs to be. So after you've set all of this up, you should have a query that's provisioning. It's going to take about 5 minutes to bake and actually set up. So I'll take this opportunity to either answer questions or we can review some of the recent changes to TigerGraph's GDSL, which is our graph data science library. And let me just check feed loop here in case there's anything. Okay. So I think I'm going to go over the TigerGraph GDSL in the meantime, while some people are still setting up their instances. So this is our repository. It's the TigerGraph sponsored repository that contains all the latest algorithms that we've developed. It's a pretty readable and easy to manage structure. The README has been updated to be a bit more readable. It contains a nice big list of all the algorithms that we feature. And in the algorithms subdirectory, we can actually see all the categories that we offer, like centrality, which is great for finding influential entities in your graphs. We have classification, which is a whole host of academic graph problems, but they do have practical business applications. Community algorithms, which are great for clustering entities with similar properties. Embeddings, which generates numerical features that you can use in downstream ML tasks. And then path algorithms, such as like shortest path or maximum flow, if you're trying to optimize something. And then similarity algorithms, which we're actually going to feature in this workshop today. That's if you have two vertices and you're trying to figure out how similar they are in the graph. Typically, you're going to want to actually use neighboring vertices to perform these similarity calculations. And then topological link prediction, which is very similar to similarity, but it's a slightly older class of algorithms. They're fairly simple, but effectively, if you have two vertices in a large network and they share a lot of neighbors, then you can make some type of prediction about whether or not they will also share a link. So those are all the categories that we feature. We just had a big update that pushed like 20 plus algorithms to the repository. So you guys can check all of those out. And hopefully over the course of this workshop, we might see some of them from the GDSL. So once you have your instance set up, oh, I should have clicked start here. It's going to take a minute to start up. And then once your instance is started up, then we can actually open it up in Graph Studio. I have this other Graph Studio tab here for a practice session, so I can X out of that. Then once our instance is started up, we can get to work. And if anyone has any questions, feel free to ask in the feed loop chat. There we go. So the instance is finally warmed up, and we can hop into Graph Studio. And now this comes pre-installed with the schema and some base queries that we're going to want to explore. But we'll start with a quick explanation of what this schema is and what it represents. So we have account information with all of these features here. Now, with TigerGraph, you can represent some of these features as properties, which are attached to the actual vertices, as you see here, like first name, middle name, last name. Or sometimes it's very useful to represent these properties as actual vertices in the graph attached to these centralized entities. So we have IP, email, last name, etc. We also have this right side of the schema, which represents user interactions with videos. So we have the video play event, which is an intermediate vertex linking account vertices to videos. Now, this is a very common schema structure that you'll see when you want to represent a multigraph. So a multigraph is a graph in which two vertices share multiple edges. Now, in TigerGraph, by default, we we don't have default multi-graph support where you can have multiple edges from account to IP. But we do support this schema structure, which involves intermediate vertices. And you can have these multiple intermediate vertices to connect the account to the video to represent multiple interactions. You see very common things in like banking databases and things like that. So that's the schema that we have right now. We can navigate to the map data to graph page to see that our data sources are already set up, and we have these data mappings already set up. And then in the load data page, all we have to do is click play once it's ready, and it will load our data into the graph. So the starter kits are very useful for these quick and dirty presentations. And once these are finished loading, we should see all the statistics on the right-hand side of the screen. And John has just dropped into the call. Hello, John. Okay. So we have all our statistics on the right-hand side, so we know it's all been loaded into the graph. And then we can check out the write queries page. So these are some queries that come pre-packaged with the starter kit. So let's investigate them, let's break them down, see what they're trying to accomplish, and then figure out how we can optimize them, modify them. Now we can build off of this use case and incorporate new algorithms into our workflow. So the main thing here is the main query. So I'm going to assume some basic familiarity with GSQL. If I'm moving too fast or if I'm covering topics that you don't understand, just post a question and or I'm sure anybody in chat will be happy to answer them. So here we're grabbing all of the account vertices, which are these centralized entities. This step is just clearing any of these same owner edges. So the same owner edge here is very useful for an entity resolution case. The actual use case that this starter kit is meant for, as the name implies, is entity resolution, where we have multiple disparate account vertices, and we're trying to correlate them to the same account or the same user. And we can represent a connected group of users, that is, accounts that all represent the same person, by connecting them with this same owner edge. Now, just as a formality, this query is clearing them out of the graph, and then it's running a select statement over all of the account vertices. And then in the accumulator clause, in this case, it's just performing a parallelized computation for each vertex that we're visiting. And then it's calling this subquery, which is account matching. And it's passing as arguments s, which in this case is an alias for the particular vertex that we're visiting at that time. And then we're also supplying the threshold parameter. The threshold parameter we'll see in the actual account matching subquery. So let's go to the account matching subquery and see what this is actually doing. So we have here the input account, and then we have the threshold. As we just saw, those were the parameters that were passed in. We have an accumulator here, which is score. We see from the single @ sign, this is a local accumulator. So this is a runtime attribute, effectively, that's attached to all of the vertices that we're running our query over. So we are starting out with a set, which just contains that input account. Then we're doing a quick traversal over all of these edge types. So looking at this query right now, this is something that we could probably improve. Maybe, let's say in the future, maybe our schema changes. Maybe we want this to be more extensible or a bit more flexible. There are ways that we can modify this query so we don't have to hand write this list of edges every time we want to run it. Likewise, we see all of these edges typed here. So if you're copy and paste, even if you're copy and pasting this thing over and over again, there's still room for manual error, especially if your schema is changing. But in this second select statement here, we also have this big case when clause. This is also a bit of manual coding that we could probably simplify. And what it looks like this query is doing is we're starting from the account. We're visiting the attributes, which is attributes spelled here. We're traversing all of these edge types. So we see has IP, has email, has last name, has phone, has address. These are all the edge types here in the schema. And we're going to these, what are called feature vertices. Then we're traversing from these feature vertices to, this syntax here indicates that it's to technically any type, but in this case, it will only be to another account vertex. So we're traversing to account vertices that share these feature vertices. So in other words, accounts that share the same IP or share the same email or last name. And you can see how this is starting to form the basis for entity resolution. If we have accounts that share all the same features, then we can presume that it's the same user. Now, what this query is doing with this case clause is it's associating a score with each of these edge types. In other words, if these two vertices share an IP in common, it adds +2 to that local score accumulator. Or if they have the same last name, a +3. Now, I don't know how the original author came up with these scores, but for now, let's just assume that they're empirically correct, or empirically the best things to use for entity resolution. And then finally, in the post-accum clause, which in this case is going to be performing another parallelized computation over the, in this case, the target vertices. We're checking to see if the score is greater than the threshold. In other words, are these entities similar enough? Do they share enough of the same features to warrant being marked as the same entity? And if so, then we use this insert into command to insert a same owner edge, which includes the account, the input account as the source, and then the target account as the target. And then we have the score as the value. So we notice in the schema that it does have an attribute called score, which is a float. So the ultimate output of this main query GSQL file is that we're grabbing all of our counts, we're doing some entity resolution using these shared features, and then we're generating same owner edges between accounts. So I think the first thing that I want to do and that I want to point out is that while this subquery structure works, oh, hang on, I just got a message in the chat that we can't hear anything. Uh-oh. Emily and John, I don't know if you guys can hear me.
I can hear just fine. You just need to enable your audio.
Is that to the commenter that they need to enable their audio, I assume?
Yeah, I mean, you can't hear anything.
Yeah. Okay, yeah, I hope the audio is getting through. Otherwise, this will be a very boring presentation. Okay. So this query structure is okay, but it uses this subquery, mechanism here. Now in GSQL, this doesn't actually fully leverage, it doesn't leverage the full parallelism that TigerGraph is capable of. So we're actually going to want to rewrite this pair of queries. And I guess let's get to it. Let me just show you how we might want to restructure this query. So it's all in one GSQL file. It leverages TigerGraph's full parallel processing abilities. And we can also make the code a little bit cleaner. So let's just call it account matching. AP is a common prefix we use for all pairs. That typically means that we're grabbing every vertex and we're performing some computation for all pairs in the graph. So let's create that query. We'll add it here. Let's start by just grabbing this code, and then we'll work by modifying this code base. So we'll copy and paste into this new query. Let's rename the query name so that it matches our name here. We also don't need to pass in an input account because this is no longer a subquery. This query is going to start by actually grabbing all of the account vertices. So account star, that gives us all of our accounts. So I think the first thing that I want to do is, well, let's leave this hard coded for now, and then I'll show you a quick trick, a quick like pattern that we use to make these long lists of edge types a little bit cleaner. So here we go. So the first thing that I'll want to do is let's create a map. So let's create a map accum. So right now, with the original definition, it was okay to just have this single local accumulator. But I think what we want to do is we want to start from these account vertices, want to traverse to our features. And then those features will want to contain on themselves the accounts that traversed to them. So in other words, they'll have a map of the accounts that traverse to them. And maybe that map will contain the score, these empirical scores that we've written down here. And then those feature vertices will traverse outward back to the accounts. They'll pass those maps that contain the accounts that originally traversed those feature vertices. And the accounts will then look at those maps that they've just received of other accounts that share those features. And then we can perform this same owner computation. So let's start doing that, because that's a lot of information. We'll do it step by step. So we'll start with a map accumulator here. And this will be mapping a vertex to a sum accum, which will be a float. And this is functionally equivalent to the score. But because we're doing all pairs, we are going to want this map accumulator. It's still going to be local, a local accumulator. So it's going to be attached to all vertices. Let's call it a score map. I think that makes sense. And then in this clause here, so this is an indentation style I like to use because I like all of the clauses to be lined up. So let's do it in the accum clause. In the accum clause here, we'll want to add something to T's map. So it's going to be T's score map, and it's going to be plus equal. And let's alias start here, because we actually want to use that vertex. And then S, and we're going to want to map to whatever score value is appropriate. Okay, so instead of just copy pasting this code, I actually want to write this in a more, I want to write this in a cleaner way that doesn't have so much duplication of code. So let's define another global map here. Let's call it weight map. In other words, weight or importance of these shared features. Now, these computations that we perform on accumulators don't just have to be performed within accum or post-accum clauses. We can perform them on the global level here. So let's do weight map plus equals, well, let's do has IP. Let's just write it here. .2. Then we'll do has email. Make sure we get the capitalization correct. 0.3. I'm effectively just copying the values here. And the reason why I'm storing it in this map is so we can just reference this map. And this is a very common coding paradigm that you might see in a high-level programming language. And since GSQL is a high-level programming language, we're going to use it here. Has last name. And if you are a faster typist than I, then you can go ahead and finish this without me. Has phone, 0.2. Has address. Another chat. There is no audio. Please join audio by clicking the left bottom icon. Emily, do you know what that's about in the chat?
No, I mean, I think we're good. I've confirmed with multiple people that they can hear you. So
Great.
Just keep on going.
Okay, cool. So this should finish the addition to our weight map. Oh, we also have has device. So let's put that in. 0.2. There we go. Okay, so we have this weight map here. We're not going to need any of this code. So that's a relief. But here, we're going to want to, what we can do is we can get the type of the edge. So we can do weight map dot get e.type. And that will take the string, will perform a match. Oh, what are we going on? What are you doing here? Let's see. Oh, sorry, it's not this global map here is not a map from vertex to float. It's actually going to be a map from string to sum accum float. There we go. No more compilation errors. So what this line is doing here now is it's using this weight map to basically store the score for each of the accounts that have traversed those shared features. The second step is going to be taking those maps, propagating them out to the other accounts that share those same features, And then the accounts are going to use that map to perform the same owner computation. So right here, we're traversing from attributes to here. We can ignore this filter. And in the accum clause, we're going to want to re-add the accum clause here. Let me also indent this because I like this being tab aligned. There we go. Now in the accum clause, we're just going to add attributes. We're going to want to alias attribute. S here is a standard that we use. So t dot at score map plus equals, we're going to go from s. Actually, we're just going to add s dot at score map because we've just updated the score map of the attributes in this previous select statement. And now we're going to update t score map with that same thing. The way these accumulators work is that you have each of those features that have a map containing the accounts that have gone to them along with the weight associated with that feature. And then they all add those maps back to other accounts, and it will sum up those scores. So computationally, it's the same as what the code was doing before, but it's a lot cleaner. And in this case, we're doing all pairs instead of just single source. I'm going to get rid of that semicolon. And now in this post accum clause, we're going to want to iterate through this score map and perform this same owner computation. So let's do a for each. We're going to want to get the vertex, and we're also going to want the score. In Python, this is like iterating through the items of a dictionary, getting the keys and values in iteration. And we're going to want to do t dot at score map, and then do the following. We'll want to insert an end here. And we'll want to indent this and move that semicolon. I missed an in score map. There we go. So we don't want to have a vertex compute this for itself. So we're going to want an and where v does not equal t. So we're no longer using this input account. Now, I think we might run into an error here because, yeah, exactly. So the same owner is valid from vertex types, don't cover all vertex types. So if you notice, we're just using vertices. These vertices could technically be any vertex type. So to keep the linter or the compiler happy, we can specialize this template here by doing vertex account. We know that we're traversing to account vertices. And now the compiler is happy. So this code should be doing what we want it to do. Yeah, we can install it, or we can just run it in interpretive mode. I like to install because it maximizes efficiency. On the back end, this is just pre-compiling the query from high-level GSQL code to parallelized C++ code. So let's give it a minute to install, and then we'll run the query. If there are any questions in the meantime, now's a good time to ask. I imagine when the recording is released, we can just edit out these wait periods. Okay, query is installed. We can use any threshold. Since the recommended threshold of the original algorithm was 0.6, let's just run it with 0.6. And let's run the query. And it's printed out all of our results. For much larger graphs, you're not going to want to print them all out if you have just tons and tons of them. And here we see these little vertices. If we expand them, actually to explore the results here, let's go to the explore graph. Yeah, let's grab some vertex types. The account vertex. Double click. Let's see. Uh-oh, it doesn't look like we've inserted any same edges here. Let's go back and let's check the code. This is all part of the process of solutions architecture, iterative programming. So let's see here. Going from our start vertex, traversing through these edge types, going through the target. Oh, we have a question here. Does the usage of the for loop under accum post accum give better performance than outside? So the for loop, no, not really. The for loop is still just a linear scan. The code doesn't take the for loop and automatically parallelize it, because that would be a very non-trivial task for the compiler. And generally, we try to avoid using for loops under the accum and post accum clause, because that means performing a linear scan for every vertex. But in this case, we don't have a very large data set, and it doesn't look like it kind of looks like a sparse, or the graph is on the sparse side. So it's okay performing a very short linear scan for each of the vertices. And then we have another question here. Is the Graph Studio tool open source? Do we run scripts as a cloud service, or is it better to install the application locally? I really appreciate your feedback. The Graph Studio tool is not open source. I know it's written in Angular. I don't know if John is here, if he could talk a little bit more about Graph Studio. But no, to my knowledge, it isn't open source. Although the outputs of TigerGraph and the API of TigerGraph is very, very expressive. So writing applications that use the inputs and outputs using the API of TigerGraph, you can create something like similar to Graph Studio with like full customization.
Yeah, and you can also go to, if you go to dl.tigergraph.com, you can download the free enterprise version with Graph Studio. It's just Graph Studio as a product is not open source in itself, but it's free to use.
Yeah. And then is it better to run scripts as a cloud service, or is it better to install the application locally? So with a cloud service, well, you'll get a bit of latency technically. If you want immediate output on the instance on which you're running it locally, there's no network latency. And if you run it through the cloud service, you have to make under the hood API calls. So you get network latency, but it's, especially for presentations like this, it typically doesn't matter whether it's in the cloud or if it's locally installed. I definitely prefer TG Cloud for setting up like quick demonstrations like this, though. But that's a good question. Okay, so let's see what's going on here with it not generating our same owner edges. So we can actually look at the output here. And we can look at it in JSON format, which might be a little bit easier to read. Or it might be a whole lot of text, in which case it's not going to be easy to read. So let's switch back to the graph result, mouse over one of our vertices, and we see here the score map accumulator. So it actually does contain the IDs that we're looking for. So we have this account 834, which connects to 234, and it shows the similarity score, 534, and it shows the similarity score. So somewhere in our code, we've made some kind of logical error here, such that we're not inserting these edges. So let's see. We should be inserting from V to T. Let's see here. Maybe what's going on, and that the compiler is not telling us, is that we need to specify this as an account vertex. The linter might not be catching this because this is kind of a tricky syntactical issue. Because we know that the accumulator is getting updated. And so, oh, 1 second. Okay. Yeah, let's try it this way. Now specifying the account as the target vertex in the select statement. Let's see if that adds our edges. I'm just going to run it in interpreted mode. Don't have time to wait for installation. Once again, print out a whole bunch of vertices. Let me deselect them and then double click to expand this vertex. We're still not getting our same owner edges. Interesting. Oh, very stupid error here. I was referencing the old local accumulator at score that was defined in the previous version. We can actually just trash that accumulator totally. We can do that. There we go. Because what we actually wanted to use was this score value that we retrieved from iterating through our score map. So this is almost certainly going to work. We can run it in interpreted mode. I'll answer that question in just 1 second. So again, in interpreted mode, get a whole bunch of output. I'm much more confident in the likelihood that this will work. We can click off our vertices, double click to expand. And there we go. We see the same owner edges with the appropriate score value on the edges. Phew, okay, got through query number 1. Let me answer this question real quick and we'll move on to the next step, which is going to be weakly connected components, which is a really solid algorithm to learn for entity resolution. So this query here is, does the usage of multi-level, that is like subqueries, impact performance much? Can it help in improving performance by dividing tasks through subqueries and then calling the subqueries from accum clauses? Or would it add too much load on performance? Should one stick to one long GSQL query or distribute the load to subqueries? That's a great question. So with the internal testing by the engine team, or it was either engine team or language team, they figured out that it either wasn't using all of the available threads when it was invoking those subqueries, or it was, but those subqueries were like hogging, taking control of the threads, and maybe there's a bunch of like context switching going on in the back end. In either case, this subquery structure has basically fallen out of favor unless the part of the code for which you're invoking the subquery is like not a bottleneck of your code. It's very tempting to basically take a really complex piece of your algorithm, relegate it to a subquery, because it makes your query structure cleaner, and it looks like it might distribute the workload more efficiently. But we've actually found that it doesn't properly parallelize when you use the subquery structure. I'm not, I haven't worked on the architecture, so I wish that I could give you a more, a stronger answer as to what's going on infrastructurally. But the short answer is that the big, long, flat GSQL queries are going to be fully performant. They're going to make proper use of all the threads. And you don't have to worry about whether or not it's going to distribute the load efficiently. But yeah, that's a great question. And it was only something that we found out after doing a whole bunch of testing. Yeah, so, and let me know if you have any further questions about that or about anything else really. So I think the next step that we'll do here, so this is great. We have accounts and we have these same owner edges, and let's do explore graph to get a little bit cleaner with the output. Let's grab some vertices. Let's grab like 15 account vertices. Then we can go to the expand from vertices tab here. And we don't want to expand through all edge types. Let's only expand to the same owner edge type. And let's see how connected they are. There we go. We can rearrange our graph here. Oh, hang on, Zoom is getting in the way of my UI. We can rearrange the graph here. And we've got a whole bunch of connected graphs or connected entities. And I think this is a quick thing. If you hold and drag, you can select a whole bunch of entities at the same time. Let's click expand again, only going through the same owner edge. And yeah, so in real life data sets, you're not going to get something as clean as this, a bunch of strongly connected triangles that all represent the same entity. But in this contrived data set, that's the output that we're getting. In real world data sets, you'll have to resort to a whole bunch of heuristics and stuff to look at the shared features, make some rules to rule out certain pairings of entities. But in this case, it's nice and friendly, and we can get away with just doing this simple shared feature matching. But the next thing we want to do, this is great and all. We have a bunch of shared accounts. Let's actually represent those shared accounts as like merged vertices, because part of working with the graph is designing your schema optimally. And let's say we wanted to write some computation that took a single entity that is the combination of all shared accounts here, and we wanted to do some computation on the graph. Now, our code could get kind of messy if we have to deal with like clouds of vertices instead of just dealing with a single merged vertex. So let's make that modification. And then we're going to use the weakly connected components algorithm, which we can get from the GDSL, and we can actually create those merged vertices. So first, we're going to take a look at the schema. This account vertex is nice, but I think merged accounts kind of represent, they represent something different semantically. So let's actually add to this schema. Let's call this thing merged account. And the standard, do we do camel case? Do we do snake case? For types in TigerGraph, we typically prefer snake camel. So capitalize your type names and use underscores for spaces. And let's put that through. Let's represent the ID as an attribute, because I can imagine us using that in a future query. We have merged account. And then we're going to create an edge from account to merged account. So I noticed that it's actually 2:30. This is pretty sparse on content just because we got started late. Emily, I don't know if you want, if you want us to keep going, because I have plenty more examples that I could go on forever. But.
Yeah, 11:45 is when the next session will start. So you can go ahead and continue if you want. Sure.
Yeah. So let's do this next part. We'll get to connected components. That will be a good place to start. There's plenty more you can do with entity resolution, but this is a good sample. So we have our merged account, and we also have account. I'm going to create an edge type between them to show that this merged account has some relation to the original entity. So let's call this thing merged into. That'll be good. It doesn't have to be directed because these are heterogeneous vertex types. We know that whenever this edge is going to exist, it's always going to be in the direction of account to merged account. So we don't have to make it directed. I don't think there are any attributes we need. Obviously, you can modify the schema at any point. It's very flexible. So let's add that, and then we can publish our changes. Now I know on these TG Cloud instances, sometimes changing the graph schema can take a little bit of time. So maybe while that's updating the schema, I can do a quick breakdown of what weakly connected components actually does and how it's useful in entity resolution. And if there are any questions in the meantime, obviously feel free to ask. So let's look at community here. And then we want connected components. So strongly connected components is for directed graphs. In this case, we have weakly connected components, since the same owner edge that we're going to be using is undirected. So first, I'm going to explain the concept of a component. It's pretty simple, but just in case you don't know, let me annotate really quick. Okay, so a connected component in a graph is a set of vertices that are all reachable from one another. In other words, there is a path from any vertex in this set to any other vertex in this set of nodes. So this would be an example of a connected component. This node here could traverse there, and then it could traverse there, and then it could traverse there. It can reach all of the other nodes. And the same holds for all the other nodes in the component. And if we have another, a separate, a distinct connected component, it'll be like this. None of these guys have any paths connecting them to this other connecting component. So it's a pretty simple concept. But in entity resolution, it's useful if you have, like in our case, clouds of accounts that are all connected and they don't share same owner edges with any other accounts. That connected component, in other words, represents one merged vertex. So we have this algorithm here, weakly connected components. We also have weakly connected components, small world. Small world is for a particular type of graph that is not going to be featured here. So we'll just go with the standard weakly connected components. So we have the code here. Now these algorithms, they can be remotely installed either through the TigerGraph driver or with a TigerGraph CLI. But when you're just doing if you're just iterating rapidly and just want to get moving, copy and pasting from the repository is pretty fast. So I think that's what we'll do today. Okay, great. And the schema change job finished. There we go. And we see our merged account here. Let me go back to the design schema page just so we can see it. We have merged account and then merged into connecting our accounts to those vertices. Let's go back to the query page. And then let's add this weakly connected components. So the name, if you didn't notice, was TG weakly connected components, WCC. So let's create that. Then let's just paste in our code. So here we go. So most, if not all, of the algorithms in the GDSL are designed to be schema free. That means that they're actually agnostic of the particular schema of your graph. You don't have to modify the queries in order to get them to work at first. Now, I think we are going to modify this a bit in order to create those merged account vertices. But for now, let's just stick with the current structure and see what we get. So you can save that. We need to install the query, which will just take a minute. And maybe after we run it, I can show you the actual structure of this code, show you how it works. Because this type of format, the structure of this code is actually excellent for an MPP architecture, a massive parallel processing architecture, which TigerGraph is. And it's a pattern that's used in several other algorithms, such as label propagation, which is actually a community detection algorithm. So let's just wait for it to install in the meantime. Okay, and the query is installed. So we can run it. So with these schema-free algorithms, what we do is we parameterize the types that we use. So v-type here, as we can see in the comment, it's the actual vertex type that we want to traverse. So in this case, we want to merge all accounts. And then the edge type, we want to do same owner, because that's the relevant edge type we're going to use. I think the output limit is fine. Printing out 100 vertices is no big deal. And yeah, let's also print out the accumulator as well. So we can run this first. So that's pretty good. And we see, you can see there in the box what the connected component ID is. The connected component ID should be shared across the neighbors of that entity. So if we double click on that entity to expand it, which hopefully it works if my Mac is not dying. There we go. Let's expand this guy. Here we go. So we have this same owner edge shared with these other accounts. So the connected component here is 692.06071. And oh, right. it's not gonna print out the vertex because it's not going to print out the accumulator. This one will print out because this vertex was already printed out. And we see that it does have the same connected component ID of 692.06017. So that's great. We've represented this as an accumulator, but let's actually create these merged account vertices. So in order to do this, we're actually going to want to modify this query a bit to actually insert those vertex types. This does feature the ability to update an attribute So in other words, let's say our account vertices had some attribute that represented connected component ID. We could specify the name of that attribute and then set that, specify that parameter, and then it would update it in our graph. And then we could use that connected component ID at a later point. In this case, I don't want to, at least I can't modify this global schema. So we'll get around that by just modifying weakly connected components directly and then adding that merged account. So let's see here. So we're going from start, we're specifying the connected component ID, which in this case is it's a number, and it's the get VID, which is the internal numerical index that TigerGraph uses to reference that vertex. And then we propagate our internal IDs. So we're going from our start vertex, which in this case is every vertex of that vertex type that we specified, traversing across the specified edge type, which in this case is same owner, to the vertex type, which is account. And then we propagate the connected component ID with this plus equals clause. So target CCID plus source CCID. CCID is a min accum. So whatever number it has in an addition operation, in other words, if the right-hand side is less than the left-hand side, it will overwrite the left-hand side. If the left-hand side is already less than the right-hand side, then it won't overwrite it at all. And so we perform this iteratively until this having clause here basically filters out vertices that don't match the condition. In this case, the condition is CCID does not equal CCID apostrophe here. Now apostrophe, this is some GSQL dark magic that lets you reference the previous value of an accumulator. It's shorthand here for basically saying if the connected component ID hasn't changed, then we filter it out. And we keep iterating until none of those connected component IDs have changed. In other words, they've stopped propagating because they're all equal in one component. And then we're done with the algorithm. So that's how we get those, that's how those accumulators are updated. So let's insert a bit of code here. Let's insert a bit of code to actually update, to actually add these merged accounts. So let's see, where should we start? Let's see here. Let's also check the schema about these merged accounts. So they have an ID, which is a string. I think what I'll do is I'll start by grabbing all of the accounts. So let's do accounts equals account.star. This is a simple statement to just grab the accounts. And then we'll want to do some kind of select statement to figure out what their connected component ID is, and then create an edge between the account and the merged vertex. I think this would actually be pretty simple. So let's go accounts equals, I like this indentation method, select S from accounts aliased to S. Then in our post accum clause, this could also be done in the accum clause, doesn't hugely matter. Now we're just going to want to insert an edge. So insert into, let's do merged into, that's the edge that we want to specify. And then values. So if you're not familiar with this syntax, just you can just look at this example and it's pretty self-explanatory. Now the arguments that we provide when inserting an edge are the source vertex, then the target vertex, and then any attributes as follows. In this case, there are no additional attributes on that merged into edge, so we can just specify the source and the target. In this case, we just want to specify S, which is an account. And then we can actually just provide the expected ID of the merged account. So we can do s.at CCID. So we're going to get a little warning from our linter here that says that the primary ID type is string, but the expression type is min accum int. Now, we can actually just ignore this. The GSQL compiler is smart enough to know how to typecast it from an int to a string. Now you'll notice that we're not actually directly creating the vertices, we're just inserting the edges. And this is okay in this case. When we insert this edge and we specify this ID, if the vertex doesn't already exist, it will just automatically create the vertex. So I think this should be good to actually create these merged into vertices. So let's save that. And if we run into any bugs, like maybe because we're using the minikube in a weird way, we can just go back, iterate, fix it, and run it again. But in this case, let's install. Take about a minute. So this is the last part of the presentation. I know it's 2:45. I hope it's okay if I just go a minute over just to show the results of this query.
Yes, please continue.
Great. Okay, now it's installed. So we can run the query. Once again, we want to specify account as the vertex type. Same owner as the relevant edge type. I think this print limit is fine. And we've added our new code to insert those edges. And let's run the query. Okay, so we've run this query. If we double click on one of these vertices, hopefully my Mac responds and actually expands the vertex. There we go. Do we have it merged into? Yes, we do. We have this merged account vertex here. If we double click on that merged account, so let me select it and double click. Please let me expand it. Let me do this from Explore Graph. This will be easier from Explore Graph. Sometimes the graph display in the query thing is a little slow, especially when I've been running on this computer for a long time. So let's just select the old vertex. Let's expand from vertices. And let's expand through the merged into edge. There we go. Let's rearrange our graph to make it more readable. And there we go. We've got a whole bunch of merged accounts which match those entities. So they basically represent those shared entities. And if we take one of these entities and let's expand them through the same owner edge, like so, we can see that it is indeed the merged account of all of those same entities. So yeah, at this point, you can let your imagination run wild of what you do with these shared accounts. Maybe you can compile information about what types of videos they watched, because as we saw, that's something included in the schema here. We can take these merged accounts. We can look at maybe the videos that they've watched and see shared videos between these merged accounts, make recommendations based off of those shared features that they have. And there are obviously tons of other applications here. And it should be noted that this type of entity resolution use case, where we want to traverse to these shared features and do this type of similarity calculation, this is really only possible at scale with a graph database. It's not really feasible on a relational database once your data set gets large enough, because those traversals from account to all those other entity types is really just joining tables in a relational database. And very quickly, that can bring the whole system just down. So in a graph database where those edges are first-class citizens, that type of traversal is easy peasy. So yeah, I think at this point, that's the gist of what I wanted to show with entity resolution. I know we ran into technical issues and I had a stupid mistake with the with the syntax. But I hope this has shown you a little bit, a simple use case about entity resolution. And if you have any further questions, just feel free to ask and I'm ready to answer.